Try that. All right, that's better. Okay, good. All right, so welcome everybody. I can see that our three panelists are here, and so this will be very much, we all saw yesterday how nicely Ed ran the discussion panel, and it was all very measured and very scholarly, and this will not be like that. This will be the internet content you come for, all the reasoned debate of that you expect in these kind of things. So the format's a little bit different, and I should start by thanking the organizers for running this conference. It's been a very pleasant one, and thank the panelists for joining us. You'll see who they are in a second, and thank you for coming, because I know that this is different times of the day, different places in the world, and it's not always easy to be here at the same time, but it does make a difference to be here and talk face to face. So what I'm going to do now is I'm going to show some slides, very few slides, just to kick off the topic, and to state kind of what the procedure will be, and then I'll turn things over to the panelists, and then we'll have the what hopefully will be most of it will be the general discussion. So let me see if I can successfully share my screen here. So let's okay, so that's not quite what I wanted to show you, so let me try something fancier. Okay, I think that's good. Okay, so our topic is that we have been assigned is obstructions to UV completion, which I'm going to modify in a bit, just as you'll see. And our three panelists are Gary Hsu from Madison, Eva Silverstein from Stanford, and Andrew Tolley from Imperial, who all have great expertise to bring to this discussion. And I can kind of see in the audience there's lots of other expertise there, so I'm expecting a very spirited debate today. See if I can advance my slide. So the procedure I would like to follow is after these few slides, you'll see that there's basically 5 slides or 4 slides from me. I'm going to close out with an inflammatory debating point. And rather than doing what we did yesterday, where each panelist had a question that they threw out, I'm just going to throw out an inflammatory discussion point to do with UV completions and the extent to which we can learn from them. Then the panelists will each have a separate presentation that they'll give 5 minutes or so. I'll ask people to do it in alphabetical order, because my name starting with B, I think that's a sacred principle that we should all adopt. And then we'll have the open discussion, and the discussion would also be the time when the panelists can quiz the other panelists about what has been said. And so so hopefully there'll be lots of feedback in a free-for-all. And I think the format that we've been advised to use is when the panelists are actually making their presentations, please don't interrupt them, so we can keep their time controlled carefully there. And the vigorous discussion will happen in the open discussion period. And I understand also that there's a hard cutoff after an hour and a half, but I think we're aiming for more of an hour, and then we'll see how things go. So our assigned topic is obstructions to UV completion. And that's a little bit of a topic which is like, when did you stop beating your wife? It's kind of it presupposes a point of view. And so I'd like to change the discussion to more, can UV completions usually help constrain, or usefully help constrain low energy physics? And if so, how? That's kind of a broader context, and that's kind of what the panelists will be speaking to in their various presentations. And that could, of course, include swampland and obstructions to UV completions. Of course, what we're up against in that is decoupling. Decoupling is the thing that means that most UV physics doesn't actually make a difference at low energies, and so we're trying to find ways around that. And of course, it's a two-edged sword. If we succeed in finding ways in which quantum gravity plays a role observationally, we have to also worry if we've introduced uncontrolled theoretical errors in everything we do. And so there's kind of that tension is always in the air when we have these discussions. So decoupling basically makes, here I'm just trying to put everybody on the same page. I know that this is stuff that everybody knows pretty much. It makes some predictions robust. Effective field theories are designed to extract what's robust and what does not depend on the ultraviolet details. But there are also UV sensitive questions or predictions that are made sometimes. And the go-to example always is chiral perturbation theory and QCD. And so the examples that's robust there are the soft pion theorems that pions satisfy follow just because they're Goldstone bosons for a symmetry breaking pattern. So they would be true for any UV completion that has the same symmetry breaking pattern. And an example of a UV sensitive prediction would be, say, the mass of the neutron or something. It's something which depends a lot on the more details. And so it's a many-to-one mapping from the UV to the effective field theories. And the traditional approach to getting UV information is just to choose a UV completion, and it's ask, what does it mean? And we're interested in kind of more, because quantum gravity, of course, we know less about the UV completion. We're interested in kind of the discussion is about how to generalize that framework. So the swampland hypothesis in particular, as we just saw in our last talk, is this assertion that there can exist completely sensible EFTs for which there does not exist a UV completion. And that would be very useful to know if that happens, because in this Venn diagram on the right, if you look at all the EFTs, the vision that this proposal has is that it's hard actually sorting through all the field theories that we have to find the ones that describe reality, and then we'd have a much shorter list to sort through if UV completions give us some guidelines. It's often motivated by difficulties getting specific things like the Sitter space from string theory, and in most of the context, I think, when we discuss it, we're going to be thinking of string theory as the candidate of the UV completion, the candidate UV completion for gravity, although that need not be so crucial. Important point is the blue dot here is what describes reality experimentally, and this blue dot, I've drawn it inside the string EFT bubble because that's imagining that the swampland thing is successful, and we're more successful finding the blue dot by restricting our search. It could be the blue dot's not in the string theory, effective field theory subset, in which case then we would learn that the string theory is not the UV completion. Could go either way, and I think that we don't need to prejudge that. One last point before I throw out the inflammatory observation is that there's two things that are different from the swampland hypothesis, and I only raise them because often the evidence that's proposed for the swampland hypothesis is really evidence for these two other things. And so it's worth keeping in mind the differences. The two distinctions I'm making here are, you can have sick theories, sick UV completions, which are sick in the UV. And so their sickness is beyond the reach of any sensible effective field theory that describes their low energy limit. For example, by maybe the sickness is something which can't be captured in the adiabatic approximation or something like that. And the other thing that could happen is that, and what often happens is that you have a class of theories in the UV completion where there's parameters, and for some values of the parameters, the theory is sick, and for other values, it's not sick. And you might look at that by looking at pathologies and scattering amplitudes. And in that case, it's often true that the effective field theory of the low energy limit of those theories also have parameters, and for some values, the parameters are sick, some they're not sick. And that's not an example of the swampland in the sense that it's not the sick one. The non-sick EFTs are typically have in these examples a non-sick UV parentage. Anyway, those are three different things, and the swampland is aiming at a very strong one. So now the inflammatory kickoff. So let's coin the principle of swamplementarity. That the assertion to be debated is that the more plausible a potential swampland marker is, so that's something which indicates that you have an effective field theory that is in the swampland, which is what we're trying to identify. The more plausible that marker is that it's a consequence of something like string theory, then the less useful it is at low energies. And conversely, the more predictive you have of a candidate marker in the IR, the less plausibly it arises from generic UV physics. And so I have in mind in those examples, something like the absence of global symmetries is something which very plausibly is something predicted by string theory. But it's also true that accidental global symmetries often emerge at low energies, even if they weren't there fundamentally. So the absence of global symmetries in an effective field theory may or may not be a useful clue. And there were, of course, many strong conjectures as to what could be going on in the swampland, and there's certainly debate in the literature, and we'll see today probably as to how compelling they are as consequences of things like string theory. So with that, I'm gonna unshare my screen, and then I'm gonna move to Gary and ask him to share his screen, and he'll be our first panelist. And so take it away, Gary.
Okay. Can you see my screen?
Yes.
So when Fernando asked me to be on this panel, I told him that I'm happy to contribute as long as this is not an unnecessarily contested discussion. And he assured me that if the discussion gets as contested as the US election, he would send in some South American observers to help. So let's see if he delivers what he promised. Now, the reason why we have this panel discussion is that we would like to understand how to connect the UV with the infrared. And the best we can do at the moment is through the crutch of an EFT. Now, the approaches we take may differ, but the end goal is morally the same, which is to understand what theories in the UV can say about observables in the infrared. Now, traditionally, as Cliff also mentioned, we start with what we know about the UV and construct models. We then compute, to the best of our knowledge, the effective field theory descriptions of these models. And by that, I mean not only deriving the effective action, but also quantify the next order corrections that we neglect. Predictions are then drawn from these EFTs. Now, they have had some successes with this approach, and I'm sure Eva will tell you a lot more in her segment. I certainly do not disagree, as I spend a great deal of my time practicing this approach. Recently, there has been a movement in addressing this question in a somewhat different way. Now, I promise my fellow panelists not to use the S word. So let me just refer to this as the alternative approach. So instead of working from a specific model to its predictions, to its EFTs and to its predictions, this alternative approach aims to identify criteria that separate good effective field theories from the bad ones. Good here means that there are no obstructions to UV completing these theories. Now, if you have done your due diligence, the EFTs that you are paying from string theory derived models should fall into the good category. So is this the end of the discussion? Well, the traditional approach is not without drawbacks. For one, we don't know what is the space of all good EFTs, as our knowledge is only limited by examples. Moreover, in deriving the EFTs from string theory models, one oftentimes has to make some technical leap. One can question whether we still have good control of the EFT and whether the corrections that we unavoidably have to neglect are indeed quantifiably small. So you could argue where to draw the line and whether the boundaries between the good EFTs and the bad ones are sharply defined, but I hope the existence of obstructions to UV completing certain theories is not by itself a very controversial statement. So to just drive you the point, to just drive home the point that not good, all EFTs are good in the sense above, let's start with QFTs without gravity. This is our common denominator. I don't think there will be any disagreement. So for a U1 gauge field or a scalar field with a shift symmetry, the leading interactions are irrelevant operators suppressed by some high energy scale lambda. They are parameterized by some Wilson coefficient C's. Now to an effective field theorist, these Wilson coefficients are arbitrary numbers. However, a negative coefficient, no matter how small, would violate unitarity and causality. Now, I have seen people arguing that if a theory is perturbed by some small parameter, the EFT ought to be under control. This is an example where an arbitrary small parameter can drastically change the quality of the theory. Now, gravity, of course, introduced subtleties to these positivity bounds. I believe Claudia talked about this in her talk this morning. I unfortunately cannot attend due to the challenging time difference, but it's not so hard to see why gravity would change things. For one, the back reaction on the metric modified the light cones, but more importantly, the tree-level graviton exchange diagram dominates in the forward limit of the 2-to-2 scattering amplitude, and in fact, diverges quadratically in the high energy limit. Presumably, the only perturbative way to make mild of this UV behavior is for the graviton to be accompanied by a tower of higher spin states. To my knowledge, the positivity bound for gravitational theories are not fully understood, although there have been a lot of work in recent years. And Andrew can correct me if I'm wrong, but it is not so unreasonable to expect that there are consistency constraints on coupling QFTs to gravity. And I should emphasize that these are really UV constraints, because the reason why we cannot get the usual field theoretical positivity bound is because of the violation of the Froissart bound, meaning that the amplitude grows as quadratic with the center of mass energy. And so we could not deform the contour using analyticity to constrain the coefficients of this, to constrain these Wilson coefficients. So in fact, motivated by the weak gravity conjecture, it was shown that for certain theories where this UV behavior can be tamed, instead of the usual field theoretical positivity bounds, some combinations of the Wilson coefficients are constrained to be positive by unitarity and causality. Now, this is a conference on cosmology. So what do these positivity bounds say about cosmology? For the purpose of inflation, minimally, we would like to understand the UV constraints on the EFTs, at least up to dimension 6 Planck suppressed operators, because the slower parameters are sensitive to these operators. However, there are also models where infinitely many and not just the leading operators are important. This is the case for DBI inflation, where infinitely many higher dimensional operators sums to a square root. And there are also recent extensions of this idea where the infinite series sums to a log. And models of this type with sizable irrelevant operators are interesting in the sense that they can generate observably large non-Gaussianity with distinctive shape. And in fact, the non-Gaussian features for a broader class of models, sometimes known as the P of X theories, have been computed and classified. And DBI inflation stands out as a particularly well-motivated model within this class because we can trace its UV origin. The DBI action governs the brane degrees of freedom in the small acceleration limit. But there are also other models that have been proposed. An example is K inflation. An example is given here. Other than the obvious questions of why we can truncate this infinite series when all the higher order operators are important, you find that for some few values and for some choices of the model parameters, the dominant energy condition is violated, and you find superluminal propagation. So except for DBI inflation, many of these models may potentially face with obstructions to UV completions. The question is, what are the constraints that separates the good theories from the bad ones? Now, a lot have been said about the virtues of the traditional approach, and I assume that Eva would talk a lot about that in her segment, so I won't repeat all of them here. But I think the most important lesson that we learn from this traditional approach is that having specific models oftentimes suggests interesting cosmological signatures that effective field theories may otherwise overlook. And if one were to play devil's advocate, which I won't, one can ask whether these signatures are truly stringy. But I would not go as far as to dismiss the model based on some conjecture properties of quantum gravity. I think we should not dismiss the model on the basis of some conjecture constraint on quantum gravity unless we are sure about these constraints. However, I would like to speak up for those practicing the alternative approach. With the same fairness, I think we should not dismiss the conjectures simply because they are not yet proven. In the same way that the founders of quantum mechanics did not dismiss Bohr's quantization condition, even though the evidence for it was rather thin. The power of Bohr's proposed condition on angular momenta, or conjecture, if you like to call it, is that it applies generally and not only to a few atomic transitions that have been measured at that time. It also pointed us to the right direction and motivate us to ask interesting questions. And similarly, these conjectures, if proven, would be universal. And they also offer complementary insights on quantum gravity that the traditional approach does not give us. So there have been a lot of serious work done in this direction, and calling it an internet meme, in my opinion, is not at all accurate. I feel that the discussions surrounding obstructions to UV completion have unfortunately been tainted with prejudice in a way that made the discussions not very productive. And hopefully with the new year, we will be more open-minded and be able to see the virtues of what others are doing. Our common end goal is likely to require every insight that we can get. So I would stop here. And let me also stop sharing my screen.
Thank you, Gary. That's you're in the hot seat because you're probably outnumbered amongst the organizers here. So I did that very well. So Eva, can I get you to share your screen? And
sure, here we go. Okay, let me go up. Whoops. Excuse me. Sorry, do you see that?
yes, we do.
Right. Yeah. Okay. Great. Okay. Yeah. So let me address Cliff's question in my own way by trying to indicate where I see the best directions for future progress. And the task is really daunting to fully understand quantum gravity in the cosmological setting. So this is kind of a schematic picture of what we're facing. We have some global system that may even include multiple components, a la Coleman and all the recent work on page curve calculations in black hole physics, and involves many types of local physics, all of the landscape and string theory. And within that, we have a patch that we have some observational access to. And one thing that we should keep in mind is just how amazing it is what we do, what we are able to glean from that. I mean, it's incredible what we can learn about what was going on or what was not going on some 14 billion years ago. And this is continues to amaze. Now, the connection between the UV and the IR is extremely interesting, but very, very nuanced. And the reason that there is a great debate is because of the extreme position taken early on, a year or two ago, of saying not just that the structure of quantum gravity matters, which we've been saying for years, right? That's been the subject of the landscape and its mathematical structure and implications for phenomenology and for quantum gravity more broadly throughout the history of the subject. But instead what was done was to imply that some sort of meta-analysis of all examples was completed and found that there were no examples of de Sitter space or large field inflation when that conflicts with the existing literature. And you know, that is the source of contention in my view. So I'm going to stick with the traditional terminology of UV sensitivity or dangerous irrelevance to address this question. And you know, my view is very moderate. It's not just what Gary described as the traditional top-down sort of model to phenomenology method. It's also been a long interest to work toward the formulation of quantum gravity in the cosmological setting. And these things are all related. So Gary did a great job of reviewing this kind of situation where there's a nuanced interplay between string theory examples of de Sitter and inflation and phenomenology. The motivation for that is also related to what Cliff introduced, which is the standard Wilsonian sense in which any inflation model is UV sensitive. On the other hand, as Cliff also stressed, we're talking lambda CDM. There aren't that many parameters. You can certainly describe them, parameterize them in the bottom-up language, and that is the appropriate thing to do from the point of view of analyzing cosmological data, rather than drawing some grand inference about quantum gravity from just those 6 parameters. Nonetheless, there's a very nuanced and non-trivial interplay between the two, having to do with our much better, more systematic understanding of the space of dynamics in the early universe that has come from our investigations of string theory in particular. Okay, so it's a big problem. We all want to work on it. When it comes to the nuts and bolts of what string theory does or doesn't do, it's essential to include all of its contributions. That includes the mostly positive terms in its scalar potential in 4 dimensions, reducing from a higher number of dimensions. The leading term is this d minus d crit term, which figured into the original models of de Sitter and string theory. If you turn that off with a prejudice toward low energy supersymmetry, then still the leading term is negative curvature of the internal space, not Calabi-Yau manifolds, but negative curvature. And so on and so forth. A crucial role is played by this little metastable dip in the potential coming from some kind of source of negative potential energy. That can be certain defects we call orientifolds. It can be things like Casimir energy or other quantum effects. Fluxes play a big role, as everybody probably knows, but in string theory, these fluxes are what we call generalized fluxes, which include contributions from lower form fluxes wedged with what become axion fields. And this is why the phenomenon of axion monodromy is quite general in the field, in the theory. Anytime you have a flux stabilization mechanism, generically you will have underlying that some rolling axion fields going along with the fluxes. And this package is very rich, but very structured. And so the game is to try and understand where it settles down between those two extremes. And the thing I want to stress is that there are structural constraints, but they're not as dramatic as saying that string theory does not have W equals -1 to very, very good approximation. That would be a very dramatic claim, which is not at all justified. On the other hand, we have these nuanced results about things like, how does large field chaotic inflation work? Well, it's not exactly m squared phi squared. There are these UV degrees of freedom that flatten out the potential, and there's underlying periodicity, so there's residual log-spaced oscillatory effects. Those are the things you can go and look for that have some imprint of the structure of string theory, in that case from this part, but which aren't going to give you a global sweeping statement that string theory either requires B modes or does not, or requires the absence of B modes. That would be a deeply unjustified statement to make at this point. I want to stress that in addition to this kind of list of different stress energy sources, there's a key role played by the warped product structure of the extra dimensions. And I think maybe my favorite landscape paper is this one by Mike Douglas in 2009 that laid out the form of the 4-dimensional effective potential and how the warp factor prevents certain instabilities that would naively be there. It basically screens localized sources of unbounded negative energy. I think simplifying the examples is a good idea, and we're about to put out a paper on a new class that is a bit simpler in its list of ingredients, exploring the more generic case of negatively curved extra dimensions. And within that, I see a very interesting kind of bootstrappy question, which is, having to do with the really important role of these negative energy sources internally. There's been a lot of work on things like the average null energy condition, the QNEC, quantum focusing conjecture, and so on, having to do with limitations on quantum negative energy. And in the context of the extra dimensions of string theory, we see something like that in the way that the warp factor screens what would very naively be unbounded instabilities in any compactification. And there's a lot more to say about this, but I see action items here among the nuts and bolts of the theory. Here's a little bit more about that. And in hyperbolic geometry, there's a standard kind of thin, thick decomposition where if you have a small cycle that generates a large Casimir energy that comes out negative, there's some price you pay in the overall volume of the space, which supports positive potential energy from the negative curvature. So I think there's quite a bit more to explore about the landscape and its structure. It just needs to be comprehensive and accurate. Okay, so I won't go through this. I think we heard a little bit of a review from Gary about this type of subject, and the status is more or less the same as it has been. And what I want to quickly flash through, just so it's known to everybody in this community, there are, and this again is an old idea, that there are constraints in the low energy theory that come from the UV. The classic one is the Dine-Seiberg problem, which shows that the potential energy, whatever else it does, goes towards zero either from above or from below as you approach weak coupling and large radius. And that fact reproduces what's known as the DSDS approach to de Sitter holography, where you think about de Sitter as a warped compactification to a one lower dimensional de Sitter, whose infrared, highly redshifted regions correspond to the very infrared region of a CFT on de Sitter space. This de Sitter patch that we actually saw in the talk this morning in a different way, the talk about Coleman DeLucia, this predicts two matter sectors in the sense of ADS CFT, which are coupled to each other and to a residual lower dimensional gravity. What I want to stress is that if you work from the top down with the de Sitter models that we have in their essential metastable structure, you uplift the brane construction of ADS CFT that you had in the bottom curve here to de Sitter, and just that metastable structure implies that the brane construction consisting of low energy fields on D branes gets doubled and joined in exactly the way that was predicted from this warped Randall-Sundrum-like description. And this happens because of the metal stability. A low energy person would have no problem just writing down a hard cosmological constant, but we don't have that in string theory, and that statement reproduces the statement of de Sitter holography, which by the way is also true in the DSCFT proposal, that it consists of two matter sectors coupled through gravity. And recently there's been successful formulations of this through the TT bar deformation and calculations of entropies that reproduce the Gibbons-Hawking entropy and reproduce various entanglement entropies in this problem. So the structure of the UV matter as it fits into our best understanding, our current traction on the problem of de Sitter formulation, de Sitter holography, in a way that is quite consistent with de Sitter being a good metastable configuration. Okay, so let me just basically end there. There are other developments in quantum gravity these days having to do with the calculation of the Page curve for black hole physics that bring in certain other aspects, like certain averaging that applies to gravitational calculations in these black hole systems, and certain calculations of density matrices whose leading contributions switch from one saddle point to another. That kind of stuff may enter into the problem of formulating quantum gravity in the cosmological setting. Coming back to the landscape, one thing that I want to stress is that if we just focus on the very special case of 10-dimensional starting points that preserve low energy supersymmetry and flat manifolds, so Calabi-Yaos, we are just working on a set of measure zero of this full space of of vacua and of configurations. And in fact, if you look at what's generic down this axis or the axis of different topologies, you find a proliferation of axions, you find control parameters coming from large numbers of flavors and related parameters that are completely missed in this special point of the landscape. So since supersymmetry has not been observed, and since these other regimes are much more generic, one thing that I want to leave you with is that in order to get any kind of accurate handle on what string theory does prefer or may even predict more globally, one has to address its generic behavior. So thanks. I apologize if I went on too long, but I'll stop there.
Okay, thanks, Eva. If you could unshare your screen, then
yes.
Then Andrew can.
Can you hear me?
Yeah.
Okay, great. So I actually don't have any slides, so I'll just go like
okay,
that. So I'll go quick. So I should apologize also that due to a combination of teaching and childcare issues, I haven't been able to attend most of the meetings, so I'll go relatively briefly. So Gary covered a lot of the things that I would have said. For my point, the answer to Cliff's question that he raised is that there is no doubt that there are constraints from UV completion on the low energy effective theory, because the positivity bounds are clear ones, given and they can be derived more or less rigorously in certain cases, given very definite assumptions, well, mostly generally reasonable assumptions. So for example, in the absence of gravity, the positivity bounds are pretty unambiguous. They make up very mild assumptions about the field theory, and we know how to derive them, and there's been recent work extending, I think, I wasn't there, but I think Brando mentioned about extending various positivity bounds, possibly to including full crossing symmetry and so on. So for example, we now know very definite statements. Only recently, for example, we know that, say, a weakly broken Galilean theory living in Minkowski space is just ruled out of having a standard UV completion. You need to use crossing symmetry to completely rule that out, full crossing symmetry, so it goes beyond the old statements from Adams et al. And so on. But we now know that, and that is something you can prove rigorously within a set of assumptions. Like everything, you have to make some assumptions about the UV theory, specifically the UV theory is local. And to what extent you personally believe the UV completion of your quantum gravity, whatever, should be local, that's up to you, but we can derive them rigorously given those assumptions. So in that sense, there definitely are statements you can make about low energy effective theories, given mild assumptions, I would say pretty mild assumptions about the UV completion. So I'll just say, throw in a few comments about what we don't know, we don't understand, particularly coming from the perspective of a cosmologist. What we'd really like to do is have a better statement of these positivity bounds in the presence of gravity, because obviously what we're really interested in is something like an inflationary field theory. And as Gary mentioned, at the moment, that situation is up in the air. We don't quite know how to deal with that because there's issues to do with the fact that the graviton is massless. It undermines some of the elements of the proofs in the bounds. That's not to say that there aren't bounds. There are higher subtraction bounds and so on. There are statements you can make even with gravity, but they're slightly less interesting than the ones we'd really like to make, particularly the ones that are relevant for the weak gravity conjecture. So that's slightly up in the air. We'd like to understand that. Also, I think as a cosmologist, what we'd really like to do is have statements that aren't applied in Minkowski space, but are actually applied around cosmological backgrounds. And again, they're the assumptions, one of the key assumptions of in the derivations of these bounds is crossing symmetry goes out the window as soon as you go on a cosmological background, for example. So it's not entirely clear how to go beyond that. One can imagine that you can deal with de Sitter, and I'm not sure if anybody mentioned that or you hear about that in the rest of the conference. But more general cosmological backgrounds at the moment is not entirely clear how to deal with. So that would be very interesting in putting constraints on actual cosmological effective field theories, which I suspect is what most people here are interested in. I think I'll just leave it there so that we have time for questions. Maybe that's the best thing to do.
Yeah, thank you very much. Thank you actually for all three of you for those nice summaries. And so now I think we should move to the discussion part, and I think and open up to everybody. And I can kind of see that I'm new at this running things on Zoom. I can see Alex Wickerman has got his hand up. I'll go through the ones I see, and I'm assuming I'll see them. So you want to go ahead, Alex? Can you unmute yourself? I think you're muted, Alex. I don't know if you, at least I'm not hearing you.
Hi.
Okay, we hear you now. Good.
Oh, okay, great. I don't know whether you can hear me and see me, but I hope so. At least I can see you. So great to see you all healthy. I have actually a kind of semi-question and semi-comment, which is related to what Gary was saying and to what Andrew was saying. And it's actually also related to the equation of Elias before. So as we know, the simplest understanding of, let's say, all these DBIs or P of X or KS and so all the series is actually hydrodynamics. And as Andrew said, many of the bounds would fly out of the window if you use cosmological background, but there is another detail. It's actually the background of the field itself, which is time dependent. And as in normal hydrodynamics, we know that in that case, normal hydrodynamics does not have a smooth limit to Minkowski, because it's a system which is considered, let's say, by a large conserved charge already. And there is no smooth limit when this charge goes to zero. Because the simple example, let's take hydrodynamic, and we take a density going to zero. Of course, if density goes to zero, you cannot use hydrodynamical approximation. You need to use kinetic equations. And actually, simple examples show that hydrodynamical models, like normal hydrodynamical equations, have such equations of state, which actually encode P of X. So there is no limit when X goes to zero at all. So therefore, all these bounds obtained in this way, they're very interesting, but they're only applicable for a particular corner. Basically, if you assume the origin of these things, you can guess what this low energy EFT should be. But there is no need for that. There can be much more general situations, actually.
Was that aimed at some specific, or you want a reply from someone, or?
No, it was just a comment. For example, when Gary was showing the K-essence Lagrangian, like basically not K-essence, but K-inflation, the one by Slava, Damour, and Armendaritz-Picon, he was saying that that's not well motivated. Of course, they did not provide any motivation for that, but formally speaking, I can write even much more crazier Lagrangians for P of X coming for normal physical systems of hydrodynamics. And they don't have limit X going to zero.
Okay, good.
And they're not even analytic there, generically.
All right.
So
That's
in
good.
that
All right,
sense, it's very important, of course, to have the bounds, because then we would know what can originate from what, at least roughly speaking. But many of these bounds are completely not applicable for those effective field theories, which we know they're in nature. Hydrodynamics is in nature.
Yeah, I mean, just to comment about that. So I think the kind of effective field theories you're thinking of, they're sort of well defined around cosmological solutions and not necessarily around the Minkowski solution. That effective theory probably breaks down around the Minkowski solution. And then you're absolutely right. We don't have constraints on those cases because we don't have a clear statement of how to derive these positivity bounds, or indeed any other conjecture around the cosmological backgrounds. Perhaps if it's maximally symmetric.
Okay.
Exactly.
I just want to echo what Andrew said. It's an important problem, and I'm surprised so little is known. I mean, we are not asking a lot. I mean, suppose we just want to know about leading dimension 6 operators. Even then, I don't think we have a complete story about that. And in the case of K-inflation, one can see the signals in a more direct way. For instance, if you consider particular background, you see that they are superluminal mode without going through the scattering amplitude type of argument. But I believe there's some kind of constraints. We're just not getting there yet.
So next up, I have
Right, then, but this is then.
Alex. Can I
sorry.
let someone else get in here? So Maria Mylova was she's been waiting for a while here to get in. Go ahead, Maria.
Hi, Cliff. Nice to see you. Hi. So apologies because it's a bit late here. I might be a bit funny with how I'm gonna form these thoughts. So I want to talk about. I've been hearing a lot about this gravities and emergent and not fundamental. Okay. So with regards to UV completion, is gravity being fundamental and important ingredient of this whole story we have been discussing here? And what are the implications of, if by any chance, and this, I'm gonna make this clear, is against my personal philosophy. I am a huge advocate of gravity being fundamental, just I believe it doesn't matter. But suppose that it is emergent, how this will affect all this UV completion we're discussing here, all this story.
Well, maybe I can try, or go ahead. Well, you're muted, so I don't know if you were saying yes or no, but sorry.
Yeah.
Go. Okay. Well, I mean, so the kind of prototypical example of emergent gravity is ADS-CFT, right? And so the most direct answer to your question has to do, I think, with how do we upgrade that to cosmology, and that's a work in progress. So far, it's actually half and half in some sense, not half and half, but the way we understand how to upgrade that to cosmology involves something we call semi-holographic, meaning that it's sort of like the way that Randall-Sundrum theory is holographic, if you know about that, where it's a theory which admits a gravitational, in which the gravitation in the bulk of a space-time is can be understood as coming from some non-gravitational theory, some quantum field theory, except that quantum field theory itself is cut off in some way and coupled to a lower dimensional form of gravity. So in the case of cosmological holography, any way you slice it, like everybody's approach to that has this feature that it involves a large N or large C matter sector coupled to residual lower dimensional gravity. And the lower dimensional gravity is quite a bit more tractable than the original four-dimensional gravity. So there is progress on that front. How it affects phenomenology, you know, it's still true that already in ADS-CFT that the gravity side, large radius, the gravitational and EFT description is the effective description. So it has to do with, what particular low energy theories we get out of the usual EFT plus gravity, description at low energies of what we have at high energies in string theory. So I don't know, I hope that helps a little.
So gravity doesn't need to be fundamental for UV completion to hold as it is?
It does not need to be fundamental. It could be emergent in the same sense as ADS-CFT, essentially, at least down to some residual, say, two-dimensional gravity.
Thank you.
Enrico, I see your hand up. Are you want to jump in?
Oh yeah, I wanted to say something. And I like the comment that Alex made about some of these bounds. I think it's great that we are figuring out this bound with more and more details in Minkowski, and I think that is definitely showing us the way to do it. And I think we will learn a lot on how to do that for cosmology by following the same path. But clearly, also as Andrew was saying, there is quite a bit of progress that we are still missing on the cosmology side. And one way that I wanted to share thinking about it is that, for example, for this P of X theories, you can think them of some stuff filling space. And as long as you don't have gravity, there is no problem in putting stuff in Minkowski and asking how perturbations behave on top of it. But as soon as you have gravity and you put some stuff and you ask how its perturbations behave, then Minkowski is not a solution anymore because there is stuff and stuff back reacts. And so you automatically generate some IR cutoff of the theories. And in some way, I think of FLRW of cosmology in general as providing some infrared cutoffs. All of a sudden, it does not make sense to talk about energies with infinite precision, which you could do in principle in Minkowski, but you have a finite precision with which you can tell me the center of mass energy or something like that. And that precision is set by the Hubble parameter. For example, in our universe, it doesn't make sense to talk about any energies with any larger precision than that. I think to me that also connects with what Claudia was saying earlier this morning about how to deal with these bounds when we include also interactions with a massless spin 2. And then there is this issues of this 1/T pole. In some sense, this 1/T pole is because we are insisting in telling the theory, we are on Minkowski, we are on Minkowski. But as soon as you have gravity in the game, actually it's very natural for just the metric to react and deform away from Minkowski. And as soon as that happens, there is not really a good meaning to say that there is a pole in 1/T or a pole in 1/S, because T equals 0 or S equals 0 are not well-defined points. There is fuzziness. There is just uncertainty around any energy. Just if you think of delta E, delta T bigger than some amount, as soon as you try to specify energies very precisely, then the thing is, it gets spread on a distance which is larger than the Hubble scale. So you don't even know in which Hubble batch you're talking about. And I think that is a crucial conceptual point that is missing in many of these analysis of UV consistency on IR observable. And I think we are starting to make some progress in that direction by tackling like purely cosmological objects, such as the cosmological correlators. I think one thing that I'm particularly excited is we're pretty much understanding unitarity, but I think we have like a 50-year delay with respect to where we are in Minkowski. And I hope we will be able to catch up. So that's my thought on that.
Thank you for that comment. Artur, have you next?
Hi. So I have I am kind of changing directions a little bit because I have a more general, I feel controversial comment to make. Can you hear me?
Yes.
Okay, good. So my comment is that maybe it's, well, I shouldn't say boring, but maybe not as exciting as it could be to make swampland statements in effective theories in general, even including gravity. You see what I mean is if you have an effective theory including gravity, and you see that some kind of Lagrangian or effective low energy description is inconsistent, well, then it's clearly inconsistent. I mean, you can call it swampland because you include gravity, but it's not as exciting as it could be. Let me give an example. So if you know that black holes violate global charge, and the statement is that global charge is violated, then sure, I mean, there's a clear statement, nothing is wrong with that, but it's not as exciting as it could be. I think what's really exciting, to me at least, if you have swampland conjectures or swampland statements purely in string theory, i.e. in a particular given UV completion of quantum gravity. Because in that case, I would say that at least as long as we cannot prove that string theory is the only UV completion, this is something that is really telling us something non-trivial about the UV. I mean, you could not in any possible way see an inconsistency in the infrared, no matter how well you study the effective theory. It's only that in the particular model of string theory, that some of us may believe in and others don't, that particular model cannot be obtained. And that then gives us the hope to learn something about string theory, or maybe rule string theory out, and is, I think, a more hard way of a conjecture, because I'm simply stating that you need to know the UV to confirm what is confirmed as conjecture. It's not something you can understand by studying IR theories. And I wonder whether everybody will agree or whether people perceive this as controversial, or maybe I didn't make myself clear enough. I in particular would be curious to see what Gary thinks about it. I think Gary is of the opposite kind of party, because he, of course, has very important work on using EFT arguments to prove, quote unquote, swampland conjectures.
Yeah, so what I was presenting in my point of view is the lowest common denominator of what you would call, swampland. Well, I promise not to use that word, but okay, that's the only time that it would appear. But it doesn't mean that it is the only thing. But if I understand what you are trying to do, to some extent that was done in the 80s. Back then, if that was the only thing available to us was the heterotic string, there are a lot of, quote unquote, criteria that were known based on this particular corner of string theory, like the rank of the gauge rule can never be bigger than 22. You could also prove that there's no global symmetry because of the worldsheet argument. And in type 2 string theory, you never get a standard model. There are papers written along the lines of what you suggest. The danger of trying to make a statement like this is that as our understanding improves, we may be excluding theories that we would have otherwise included.
But I mean, what I mean to say is that maybe even if you study more and more string theories, let's just imagine, just for as an example, imagine there's really no metastable de Sitter in string theory. And this is not because metastable de Sitter is inconsistent with ADS-CFT or quantum gravity in general, just because in string theory you will not find a concrete model. I don't support that opinion or that statement. I just want to give a very clear and simple example. And I think if there is any conjecture of that type to be made, that's kind of even more puzzling and crazy and exciting than general consistency issues like no global symmetry.
Mm-hmm. Right. So maybe Eva want to comment on that?
Well, I think it's an interesting question whether or not, what the theory of quantum gravity is unique. And in string theory, as you know, we find connections among all the corners that we know, and we know quite a few, right? Like the ones I was stressing at the end, large D and negative curvature, we know topology and dimensionality changing transitions that connect them to all the rest. So it's in that sense, that theory of quantum gravity is one big connected package. Other theories that might exist on their own that I am aware of are limited to low dimensions, like various forms of two-dimensional gravity might be UV complete in themselves. So I think it's just, I think underlying your question is an idea that there could be different forms of quantum gravity. We might make sort of model dependent or form dependent predictions based on those different versions of quantum gravity. Did I understand correctly?
Yes, precisely. So of course, my question aims in a way, even though I didn't say that, at the question, or the strongest possible conjecture, or maybe one very strong possible conjecture, that all consistent infrared theories of quantum gravity are UV completed by string theory. If they are consistent, then they're UV completed by string theory, not by something else. That would be a very strong statement. But I'm not sure that everybody that agrees with that, or that we have very strong reason to believe that. And I agree with you in spirit, but I never heard a technical claim of that.
No, I agree with you. Although there have been attempts in that direction that I might point out. Like I'm not going to remember all the collaborators, but I'm sure people here know better. But like Maldacena and company looked for evidence that you must have something like the tower of string states in order to avoid certain inconsistencies in gravity, just going down to basic things like having a time delay instead of a time advance in certain quantities. And that program didn't conclude with deriving that there must be something like the towers of extended objects that we know and love in string theory, but there are some sort of forays in that direction of trying to give a more principled proof of this. So I certainly agree. We don't know for sure if that was the question.
This argument is limited to tree-level completion. So if you have strong coupling effects, then it's not. This is assuming that the UV completion of gravity is weakly coupled. The argument of Maldacena and collaborators about causality bounds is limited to UV completing the theory at weak coupling.
Maybe we can also.
Yeah, no, it's not proved. That's for sure. That string theory is unique. It's not proved.
And there are also caveats that Andrew and collaborators pointed out about secular effects. That is sort of a loophole to the argument. Maybe Andrew can say a little bit about that.
Well, I would largely agree with the statement that it's just weak coupling. so if it's for tree level UV completion, it's more or less a trivial statement that they made, and I wouldn't say it was even particularly new. But if it's not weakly coupled, then it's a completely different story. And no, so it's not tree level completion, I should say. Yeah.
So Irene Valenzuela is waiting to jump in, so you should go ahead, Irene.
Okay, thank you. Yeah, well, regarding this, I agree that the very linked to the Swampland program, there is the issue of string universality. And I don't know what I find more interesting, if to have universal constraints for every FT, or to have constraints that only apply to string theory and try to find out if string theory is the only UV completion. I don't know, I think both would be fantastic. But I had a comment actually about the principle that Cliff put in his slides at the end about how, like, why the Swampland conjectures that are more useful are the ones that have less evidence, and the opposite, no? And I just wanted to say that, yeah, exactly, sorry. I just wanted to say that I don't think it's something magical. I mean, like, it's kind of expected in the sense that at the moment, I mean, the conjectures that have more evidence and we are more confident about talk about the kinematics. So it's about the absence of exact global symmetries, or the distance conjecture about exact moduli spaces. So that's the only thing that matters is kinematics. And then it's easier to prove these conjectures, while the others talk about the dynamics. So of course, I mean, it's natural that it's a second step. I mean, it's more difficult to constrain dynamics than kinematics. But of course, in order to have phenomenological implications, we need to talk about the dynamics. And that's where the interesting part comes. I think that, I don't know, at least my point of view was that first we needed to understand very well all these kinematics conjectures. I really try to understand what is the underlying reason for them before going to the next step. But now that I think we understand much better many of them, I really think that, I mean, we need to focus on these dynamics, and I think that we can make it, that we can make progress there. So it's not a matter of, I mean, that it's a matter of time, in my opinion, to continue increasing the difficulties. That's my opinion.
Thank you for that. So I have Matteo as being up next, Faziello.
Yeah, so I have a very quick question, most likely for Andrew or for Gary. And so today I've learned that, you know, these positivity bounds, they're very difficult as soon as you switch on gravity, and they stem from unitarity and perhaps some notional locality. But I have a very practical question in the, let's say, in the inflationary, in the cosmological context. And so I understand it's very difficult to derive these bounds, but my practical question is, is the difficulty of deriving these bounds in any way connected with there being multiple isocurvature fields going on or active during inflation? Or do these bounds depend at all on the way these fields, or whether these fields are, let's say, minimally or minimally coupled to gravity, or directly coupled to themselves and to other fields? Or these positivity bounds maybe transcend and can bypass entirely these properties of the inflationary Lagrangian?
Well, maybe I'll have a go at that. I mean, so if you have multiple fields, it's not a problem. You've got multiple positivity bounds. So, you know, in the absence of gravity, if you take a multi-field inflation model in the absence of gravity, even with non-minimal kinetic terms, however complicated you want it, then there's, you know, infinite number of positivity bounds. Mm-hmm. Okay, they're not all useful if we're honest about it, but there's certainly lots of positivity bounds on the multiple scattering of different states. So the complication is purely to do with when you couple to gravity, because you've got massless states in the problem. Some of the arguments, some of the assumptions you make go away. Separately, with regards to the cosmology, if you have an effective theory, so basically there's two types of scenarios. When you have a cosmological effective theory, that effective theory may include the unbroken, with respect to, by unbroken I mean the time translation unbroken state. So the effective theory may be valid both for the cosmological background and the Minkowski background. That's the sort of the traditional scenario. Yeah. In which case the Minkowski bounds automatically apply on the cosmological theory, right? So you do the perturbations around Minkowski, but it still has consequences for the cosmological solution. The other situation, which is what sort of Alex was hinting at earlier, is that there are also cases where nowadays we talk about cosmological effective theories, where the effective theory is constructed around the cosmological background and is not continuously connected with a solution around the Minkowski background. So in other words, the same effective theory does not include the time translation unbroken state. It's just valid around the broken state. In that case, then basically no one has a clue what's going on.
Oh, okay.
Yeah, but it's not a complication to do with multiple fields or non-minimal terms or anything.
Okay.
So I see Arthur being next, but I want to actually abuse my power and jump in with a quick question to Andrew. In the statement you made about the positivity bounds, do you see those as being evidence for a swampland per se, or do you see those as being an example of what the kind of thing I was mentioning in my slide about the full theory has a region which is sick and a region that's not sick, and the effective theory does the same thing? In the sense that
it's in explicit examples. You can take the P of X with the wrong sign, you can UV complete it as a multiple field model, and you find that the UV completion is sick as well. So it's just the low energy indication of the sickness of the UV theory. So it depends on your wording, right? You can UV complete every one of these theories. It's just the UV completion is sick as well.
But is there an example where there's a sign of a parameter in the effective theory, which in the one that people normally show, I could have told in the effective theory it was already sick because it was superluminal, say. Is there an example where there's a constraint on the sign of an effective coupling which I would not have known was a bad one unless I went to the UV?
Yeah, so I think these higher order bounds that make use of full crossing and so on, then you wouldn't have anticipated them.
Okay.
So I think there's not, the original sort of Adams-Adel argument, the point they made is that there is this direct correlation between the sign of the x squared term, the P of X term, and the superluminal sign. That's fine for that, but for higher order bounds, it's much more buried. So it's not as simple as saying, oh, the speed would be one way or the other. It's not that simple.
Okay. So Arthur, why don't you go next, and I have C. Sadra as being after Arthur. Yeah.
Okay, thank you. Sorry for jumping in again. Since Irene suggested an explanation of Cliff's swamplementarity, what was it, principle?
Swamplementarity, yeah.
Swamplementarity principle. I wanted to jump in with an alternative. The alternative is simply that if you have a conjecture that's mostly about the UV, that's obviously easy to prove and obviously irrelevant. And if it's more about the IR, then it's obviously much harder to prove and much more relevant. And you can see that, for example, the gravity conjecture in its most naive form can be satisfied by black holes. That's a UV thing. So that's easy to prove. It's probably true and not so interesting. There are forms of the gravity conjecture which are purely about the IR, like a light state actually as light as G times M Planck, and then it's harder, much, much harder. Similarly, the de Sitter conjecture is about the deep IR, and we have no clue whether it's true and how to prove it, or global symmetries, of course, again, are violated by black holes. So at the Planck scale. And so it's easy. So this is my explanation of your principle, which I like very much, but I think it has a very clear and not too difficult explanation.
Like all good principles, yeah. Sandra, you want to go ahead?
And I have a comment to make. A question to ask. I have a question to ask related to the previous discussion with Eva about quantum gravity models and whether we have anything else in string theory. So what if I'm very naive and I take something like causal dynamical triangulation? I just put gravity on a lattice, on some form of lattice, maybe even forbidding topology change for simplicity. And I do not insist on taking the continuum limit. I'm just happy with a lattice of size, whatever, M Planck or even below that. Does that count as a UV completion? If I can define my lattice theory, such that I can actually do calculations, which I'm not sure whether people can do that. It's an honest question. I have not thought about this deeply. Maybe anybody who could answer, I would be grateful.
Yeah, I mean, the usual argument is you have to tune many things to get so much as low energy GR out of that. Of course, you might counter that in the landscape, most of the solutions are also at high curvature, and so we have to make specific choices of fluxes and so on to obtain the large radius solution. So there, in that sense, there's also some tuning there in the string theory example.
I'm not suggesting this model is a true world or is beautiful. I'm just asking whether it could count as a mathematical example of UV completion that's not string.
I'm not sure that it is any more, I'm not sure. I think you might end up having to tune so many things that it's as if you just allowed yourself to write down whatever you want from the bottom up. But maybe somebody else could comment.
Or while people are thinking, maybe Sadra could jump in.
Yes, so it's an unrelated question, so maybe I don't know. If I can ask, so this is related to, hear me actually? Yeah, sorry. Yeah, can you hear me?
I do hear someone now.
Hello,
can you
hear me?
Can hear you now, yeah.
Sort of.
Yeah, sorry. Yeah, if I disconnected, I mean, you can. So this is related to Alex's question and follow-up discussions by Enrico and Andrew, that we have to distinguish two situations that are conceptually very different. So there are situations that I think Andrew was talking about, that you have some sort of lattice description, so you can define the S matrix and you can possibly think about the positivity bonds. But there are start thinking about the problem, and those are putative effective field theories that have cutoffs close to Hubble. Actually, this is not far from our current universe, because during inflation, the symmetry breaking scale is something of order 60 times Hubble. So it's not a million times bigger than Hubble. So in those cases, we don't even have the notion of S matrix. So, I mean, you can start thinking about correlators, but I mean, of course, for correlators, we don't know what are the rules. Starting from UV completion, what happens for the low energy correlators or late time correlators. Yeah, I just wanted to, it was more of a comment than question.
Okay, I see Alex has got his hand up.
I have actually a bit crazy question. You probably wouldn't expect anything else from me, but look, has somebody tried to use a swampland for condensed matter physics? Namely, let's take arbitrary condensed matter, right? We know it's UV completed by whatever quantum mechanics, right? And then we would look at the really landscape of infinity of effective field theory for condensed matter systems, right? Including Bose-Einstein condensations, all these electrons there, superfluids. I don't know what is there. I'm not a condensed matter physicist. Is there any way to create such bounds on the landscape of effective field theories for systems which we know are UV completed, well-defined, proper, and then see whether we can use this ideology and apply it then for something what we don't know? What do you think, guys?
I think that's
I do not know.
Amazing question, very interesting.
I do not know.
Thanks, Artur.
Where gravity is important. So.
Right, but you see, on the other hand, people like Volavik, right? They would tell you, oh, it's all whatever. What is it, like helium-3 superfluid? I don't know, but basically he was finding very similar structures there. So maybe there is a way to, I don't know, try to analyze things which we know and make some systematics. In that sense, I like what Alberto Nicolis was trying to do with many other guys, to just try to get some idea what is possible for condensed matter physics zoo, right? But I don't know, are there such things at all? Of course, it's more complicated because it's all medium and blah, 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 but who knows?
May I comment on just quick, as a joke, I mean, I want to quote Nima saying that, the world is not a crappy metal. I think it's just it's a partial response, I think, by Nima to this.
This is where we all cross ourselves, right?
Yeah, exactly.
I see Tanguy as being next, and then Rachel.
Yeah, comment. I think you can apply some of this machinery of positivity bound for certain cases of condensed matter systems when you have a notion of time translation symmetry. And so you can define a scattering amplitude, and then you can try to do this argument which was been done actually 5 years ago by Daniel Baumann and Daniel Green and Aidan Lee and other people. And you can make trigger some of the assumptions. Now you have between the superfluid and you Wilsonian UV completion, you have probably a layer of effective field theories in between. So as far as getting the precise physical understanding, we're not there yet. But I think you can write down the bounds and actually that it's a special limit of DFT of inflation as well.
Okay, Rachel, do you want to jump in?
Yeah, in fact, I was just going to say the same thing and refer to the same paper. But I think the issue is we really don't know very much about how to derive these bounds when you have systems that violate Lorentz invariance. I think if you treat Lorentz invariance as spontaneously broken, then you can maybe get a little bit more of a handle. But I think it's a super interesting question precisely for the reason Beckman said that you could test these things in low energy systems and then use those conclusions to sort of, test cosmological models as well.
And Brando, I think I lowered your hand. You had your hand up for another reason, I think, right? So why don't you go ahead?
Yeah. Well, so one thing that I want to was mentioned this paper by few years ago by Daniel Baumann and Green on the positive bounds and Lorentz breaking background, which is a beautiful paper. I think it's very interesting, and I think the main problem there is the lack of cross-seed symmetry. That just technical comment, just to say that it would be interesting actually to push forward that type of research, see what you can get out, and under certain assumption they derive bounds on the speed of sound, which I think are very important. It's a little bit of a pity that nobody else picked on that. And this was the first comment I want to make. The second one, that also I like to beg a different a little bit on how hard it is to get this bound in gravity. Yeah, of course there are subtleties, but for example, this thing about the 1/T, I think is mostly like red herring, because if you think in terms of like in physical terms, this singularity is just telling you that when the momentum exchange is small, it's transverse to the scattering plane, so the scattering light flight. So, and this is small by uncertainty principle means that these things just fly apart very far. And since this is a long range, the wave functions of the incoming states gets deformed even large distances. Now, basically what you have to do is, what I believe is that you have basically to regulate this large distance effect. But it's not that you cannot define asymmetrical properties, just have to be careful what are initial state and final state. And if you put things in a box, you regulate, I think it's perfectly possible to do this. And I think we have evidence for that, which unfortunately did not present today, because I did not have time to present, but I think, as I said, I think it's a red herring. I think it's really useful to think in physical terms what these divergences mean. And I think it means large impact parameter scattering, which is basically classical physics. And of course, we can define scattering for planets. Okay, so I think there's no issue about that. Thanks.
So I see Tanguy is being next, and we should be thinking about wrapping up soon, because I know that some of you it's 3 in the morning, or so. So what you go ahead, Tanguy, and then maybe we can make that the last one.
Yeah, I'll be quick. It was just in response of this conversation, and it's mostly an advertisement comment in response to Brando and Rachel. I think it is possible to restore cross-seed symmetry, and actually Scott, Melvin, and I we're about to publish a paper sometime this month about this. So it's just, if you're interested, I'm really happy to chat about this. I think it's possible to restore cross-seed symmetry and rigorously derive these bounds for condensed matter. Of course, yeah, there's a long way until we can do this for inflation and on this sitter backgrounds. Yeah, that's what I want to say.
So that's probably a good place to leave it, unless there's something very urgent. And I appreciate everybody hanging in this long, and it was a very interesting discussion. A little bit too civil for the internet, but what can you do? And so anyway, thank you again for the panelists in particular, and to the organizers and all of you for coming. I can't turn this thing off, and so I'll say goodbye, but then maybe Enrico, you can take over and close everything off. Thank you, everybody.
Thank you, Cliff. Also, thank you for taking the leadership.
Yeah, thank you, everybody, and see you tomorrow.